Hello and welcome. This is SFU Math 232. My name is Brenna Davison, and we're now in section 1.2, the dot product and orthogonality. So I think this lecture a little bit more difficult than the ones we have so far previously had. And what we're going to be basically doing is using our intuition of things in 2 and 3 dimensions to then define the same ideas in the n space or the nth dimension. So we'll just sort of see how we can generalize the things that we're really actually pretty familiar with in 2 and 3 dimensions. And we're going to see how we do that. And also we're going to be introducing quite a bit of vocabulary. Again, I'm going to emphasize, make sure that you know what the words mean. Okay, so here we go. We're going to start out with the definition of the norm of a vector. So that is this word here, norm of a vector. And that's really, we can use 3 ways of describing that. We could say the length of a vector v. We could say the magnitude of a vector v. And we could also say the norm of v. These 3 things all mean the same thing. So if we've got some vector, this one here is a 2-dimensional vector. It's got 2 components, v1 and v2. So we're going to ask what the magnitude of it is. So what we're thinking about is we have a vector. Here it is, v, and we can, as we've noted before, when we can move that vector down so that it is starting, its initial point is at the origin. It's still the same vector v. It's the same length and same direction. And then when we write it in this component form here, we're seeing that this here is v1, this distance here, and then this distance here is v2. So those are the 2 components of v, v1 and v2. And the way that we will write the norm will be like this. We'll have the double bar. The norm of v is equal to, and let's just take a look at this. What is the length of v? I mean, we're just going to apply the Pythagorean theorem there in that triangle. So in this triangle here, there's a triangle, we're simply applying the Pythagorean theorem, and that is the length of the vector v, or we will also be calling it interchangeably the magnitude or the norm. So that looks like this, the square root of v1 squared plus v2 squared. So now all we do is we generalize that to Rn. Okay, so we simply say that the norm of v, no matter what size, how many components it has, what dimension we're in, we call this v1 squared plus v2 squared. We compute this in this manner, v3 squared plus, and we keep going until we do them all. So that's the norm of v. This is the general case. Let's just take a quick example. We'll take some vector. I'm just going to sort of randomly pick a few numbers here, but imagine this vector here. This is in R5, and there's 5 components. And so if I wanted to calculate the length of that, or the norm of that, I would simply go about taking the sums of the squares of all of the terms. So that would be 1 squared is minus 1 squared plus 0 squared plus 2 squared plus 4 squared. I would add all of those things together and then take the square root. So let me just make that calculation. The first 2 terms are 1 plus 1 plus 0, and then plus 4 and plus 16. So if I make an arithmetic mistake, that is the square root of 22. Like that. Okay, so the norm of v here is square root of 22. Okay. There are some properties to the norm. So we're taking a vector v in Rn and k a scalar. So this is just a number, any number. Okay, the length is always greater than or equal to 0. The norm of a vector is, so the length of a vector, it can't be negative. You don't have the concept of a negative length. Your vector is always of length greater than or equal to 0, and in fact is only equal to 0. So the norm of v is equal to 0 when v is the 0 vector. Otherwise, it's going to be a positive quantity. If we take the norm of k times the vector, so we scale the vector by a factor k, then what we can compute the norm by taking the absolute value. That's important. The absolute value of k times the norm of v. Okay, so I'm just going to make a comment here. We note that our scalar is some real number, and k can be less than 0. So you need the absolute value of k when you remove it out there from the norm. Okay, we're not going to imagine if we didn't do that, then this thing here, if there was no absolute value sign there, then that thing there would potentially be negative, and then the norm is positive, so then you would have a negative thing, and then you would have a norm being negative. That is not possible. Okay, and I said this one already. Actually, the norm is equal to 0 if and only if the vector is 0. So let's just perhaps pause a little bit. We just to mention something here, and that is, let me just draw the number line here. Here's a number here, 3 on the number line. So this is just the number line that we know and love, and we're like this. You notice that the like if I look at these numbers here, and I take the absolute value of 3 is 3, and you notice that is the distance from the origin. And over here, the absolute value of -2 is 2, and that is this distance from the origin. So the absolute value of a number, a scalar, captures the idea of distance from the origin, and the norm of v captures the idea of the distance of, or I should say the length. Let me put it that way. The length of the vector from the origin. If we move the vector to the origin and measure how long it is, that's what that is. This is sort of a moving up in that. Let's just do one example here. Imagine I have a vector, a two-dimensional vector. There it is. I have some scaling constant. There it is. What this part B here is telling us that, well, let's just calculate here the norm of v. That is going to be the square root of 1 squared plus 2 squared. That's going to be the square root of 5. So that's the norm of v. I could compute k times v. K times v. That would be -3 and -6. And now I can do two things and see if they're the same. We're all happy to know that my OneDrive is up to date. Hang on. I'm all set. Can you go away then? Ah, dear. Hang on, let me just see if I have got I don't know if you can see this on my screen, how the screen sharing is working, but I've got something up on my screen that okay, there, I got rid of it. Okay, sorry about that. Okay, so here we go. We're going to compute two different ways. We're going to calculate the absolute value of k times the norm of v. And then we're going to see that that is the absolute value of k is 3. The norm of v is the square root of 5. Okay, and then we are going to go here and instead take this and calculate the norm of kv. And that's going to be the norm of this vector here, -3, -6. And that's going to be the square root of 9 plus 36. And that's the square root of 45. And that is 3 root 5. Okay, and the big exciting thing here is that this thing and this thing are the same. That's what part B is telling us. Okay, norm. Length, magnitude. Okay, distance. The distance between 2 points. So we've now got two vectors here, u and v, and we're going to talk about what the distance between u and v is, and that is the norm of that vector subtraction. So the distance between u and v is the norm of u minus v. And that is equal to taking the norm, that is the square root of the first component of the vector squared, and the first component of that subtraction looks like this, and then the second component of the vector, and we keep going until we get them all. That's going to be a minus sign, like that. Okay. I don't know. Distance between two vectors is always the positive or 0. The distance is between two things is only 0 if the two things are equal, and the distance between u and v is the same as the distance between v and u. This is saying here, we could rewrite this like that. That is the norm of u minus v is equal to the norm of v minus u. Not being entirely consistent with my type of v's I'm drawing. I will try to improve that. Okay, let's just see if we can just draw a picture of that. And that is, I would have here u, and here I would have v. And then I'm going to draw a line here, which I am going to label t. This is, of course, the two-dimensional case. And I could write here u plus t is equal to v. And that, of course, means that t is equal to v minus u. Okay, I could also, just seeing this potentially in a slightly different way, just to keep the geometry straight here, we could extend this line here. I'm attempting to draw here a line that is continuation. So this here is going to be, this line here is going to be minus u. So that is in the opposite direction of u and the same length. And then I could add minus u plus v. So I would put the minus u here, like that. So this is minus u up here. And then I would see that I would have another place where I could see t. It is the same vector, and it is here. So this is the same direction and the same magnitude. So it's there. That is the difference between those. And you can see that that's the distance between u and v. Okay, next point. So we've got norm, and then we've got distance between points. Now we're going to talk about a couple of other things. What is a unit vector? A unit vector is a vector of length 1. So here this is length 1. Length 1. So we're just going to find a unit vector parallel to a non-vector v. So what does that mean? The little picture here, you'll see as we go through these things, I'm big on seeing what's going on. So here's some vector v. There it is. And we want to find a unit vector parallel to that. So what we're looking for is a vector parallel, like that, that is of length 1. So this distance here is to be 1. And then we're going to call that u. That is going to be the unit vector parallel to the non-zero vector v. And perhaps then you can see what you would need to do is take the vector, in order to produce this value, this vector u, you'd need to take the vector v and scale it so that it was, in this case, shorter. And you would need to scale it down by the length of v. And that's where this expression comes from. The unit vector u that is parallel to the non-vector v is the vector v itself scaled by the norm of v. That's the unit vector. Okay, I want to be really clear that this is a scalar product. This thing in the bottom here is a scalar. Let's shut my email off. It's making noise. Okay, so that is a scalar. So I'm taking a this thing here is a vector, and I am taking a vector and I am multiplying it by a scalar. So this is a scalar product, a scalar multiplication. So this is a scalar product. I'm making this distinction because we're going to see coming very, very soon that the dot product is a type of vector multiplication or a vector product. Okay, so we have standard unit vectors in n space. Here they are. The standard unit vectors are we label them this way: E1, E2, E3, and E1 has a 1 in the zero in the first position and 0 everywhere else. E2 has a 1 in the second position and 0 everywhere else, and then En has has a 1 there in the nth position and 0 everywhere else. Okay, so we have standard unit vectors in two space and three space that we're used to working with, and we have special names for those ones. You will see I in 2 dimensions. You will see I, which is this vector here, and J, which is this vector here, and that's in 2D. So that's in 2D. And then in 3 dimensions, we have 3 of them, I, J, and K. And I is 1, 0, 0. J is 0, 1, 0. And K is 0, 0, 1. So they have special names. And once we move beyond the 3rd dimension, we simply use E1, E2, E3, E4, how many ever we need. So let's just draw a picture of where these vectors are in 2 dimensions. Here's our 2-dimensional coordinate system. And then we're going to have the 2 unit vectors that the standard unit vectors we've identified here. This is going to be this one here. That will be I. And then this one here will be J. Like that, and they are of length 1. So this point on the x-axis is 1, and this point right here on the y-axis is also 1. They are of length 1, and they are oriented thus. Let's just draw the 3D situation. That looks like this. We're going to label this one X, this one Y, and this one Z. So this is our 3-dimensional coordinate plane. And what we're going to do is have the standard unit vectors like here. Well, they will be like this. This would be I. This one here will be J, and this one here will be K. And again, sorry, that is not a K. This one here will be K. So again, these are vectors. Let me make that clear actually. These are vectors, and this point here is 1, this point here is 1, and this point here is 1. Okay, so it is the case that when we have the standard unit vectors, we can form any of the other vectors in that same sized space as a linear combination of the ones that we have. So what does this mean? It means if I take, for example, in the 2D case here, if I take any vector v, and that would have some components, v1 and v2, I could write this like this. v1 multiplied by the vector 1, 0 plus v2 multiplied by the vector 0, 1. I mean, you could just add this back together and see that you get this. And then we recognize that this thing here is I, and then this thing here is J. That allows us then to write it like this. This is a 1. This is a 1. Then this is V1I plus V2J, like that. Okay, so I could do the same thing in the 3-dimensional case. Let me do that one over here. Some other vector. Let me just call it say V2, and that would also have some components associated with it. 3 of them, V2 and V3, and I could then write this as V1 times 1, 0, 0 plus v2 times 0, 1, 0 plus v3 times 0, 0, 1. Okay, and then that will allow me to write this v1 I, v2 j, v3 k. And then this just scales up. The I, j, and k, these vectors, I, j, and k, the unit vectors that are on the x, y, and z axes are commonly used. We commonly see this in engineering applications and in physics applications. Okay, in the general case, in n space, so here, in n space, we have a vector which has n components. And we imagine writing it in the same exact way, v1 times 1, 0, 0, how many ever zeros we need, and then v2, and that would be capture that second component. And we would continue all the way until we had done them all, and that would be vn, and we would then capture the last component like that. And then we simply realize that what we can do is relabel that in effect as v1 times the vector e1 plus v2 times the vector e2 plus dot 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 plus vn times the vector en. Okay, so we've got the idea of a unit vector. It has norm 1, and we have the standard unit vectors, which are the ones we put along our axes. Okay, introducing a major topic, the dot product. Okay, it is also called the inner product. This is an important concept. Can't emphasize that enough. So far to date, in this course, we have not seen the idea of multiplying together two vectors. And this is going to be one of the two ways we're going to do this in this course. The dot product is one type of vector multiplication, and it's also called the inner product. Okay, so we've got two vectors, u and v. We're going to multiply them together, and we are going to get, as a result of the multiplication, a scalar, a number. Okay, and it's easy to compute. Here it is, u times v. What you do is you just take the first component of each vector, multiply them together. Then you take the second component of each vector, and you multiply those together, and you add it up. You keep going until you're done. Let's just do a quick example. If I have a vector u that looks like this, 1, 2, and I have a vector v that looks like this, -1, 4, and I decide to take the dot product of u times v, I will compute it this way. That would be the first component of u multiplied by the first component of v plus the second component of u multiplied by the second component of v. 1, 2, 4. Okay, and that gets me -7. What am I saying? That is -1 plus 8. That gets me 7. Okay. All right, so that's how you calculate the dot product. It's very straightforward to compute, and it's important to note that what ends up happening once you compute the dot product is that you have a number. You do not have a vector. So you're multiplying together two vectors, and you end up with a scalar. Okay, let's compute the dot product of u and u. So take a dot product of a vector with itself. That is going to be equal to, by the definition of our dot product, that is going to be u1 times u1. Those are scalars because those are the first two components of the vector u, plus u2 times u2. Okay, that's going to be the case for so I'm thinking here, let me just make this clear. I'm thinking here the vector u is this here, a two-dimensional vector with those two components, u1 and u2. And that is going to be equal to, or it is, u1 squared plus u2 squared. And you will notice that that is the norm of u squared. Okay, so we could rewrite that like this. The norm of u, take the square root of both sides, is equal to the square root of the dot product. All right, I'm going to take this and see if we can get a nice form. What does that equal? We want to calculate the norm of u plus v squared, and we're going to add to that the norm of u minus v squared. We're just going to do this right from the definition. So we're going to write out what is the norm of u plus v squared. Well, that's going to be the norm of u plus v, and the norm of u plus v is u1 plus v1 squared plus u2 plus v2 squared plus un plus vn squared. And I'm not taking the square root because it's the norm squared. If it was just the norm, I would take the square root, but it is the norm squared. So I'm simply adding together the squares of all of the components of the vector here, this vector. Okay, I do the same thing with this guy here. In fact, it might be a good idea to stop the video, work through this algebra yourself, and see if you come out with a simplified expression. See what happens. It's kind of that's a good exercise for you. That's just going to be u1 minus v1 squared plus u2 minus v2 squared plus dot 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 plus un minus vn squared. Okay, I'm going to add those two things together. So I'm going to add them together. This is the norm. I've written out those two things. Let me add them together. These are still vectors here. Adding them together, and I am going to, when I am adding these two things, so I'm adding these two lines here together, this line to this line right here on the right hand side, and I'm going to expand those binomials at the same time that I do this, and you can see that I'm going to get some amount of cancellation because let me just alert you to what's happening here. I'm going to notice that this thing here is u1 squared plus 2u1 v1 plus v1 squared. And then I'm going to notice that this thing here is u1 squared minus 2u1 v1 plus v1 squared. So this is going to allow me to, I'm going to expand all those things and then do all this adding, and I'm going to do that in one step, and I'm going to see that here I end up with 2 u1 squared plus 2v1 squared plus 2u2 squared plus 2v2 squared plus dot dot dot. I keep going, and I have 2un squared plus 2vn squared. I can factor out the 2 everywhere, and I can group these things in a way that might make it look obvious what I'm doing, and that is like this: u1 squared plus v1 squared plus u2 squared plus v2 squared plus dot 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 plus un squared plus vn squared. There it is, and they're all multiplied by 2. And then what is this? Now I'm going to I'm going to be considering this one and this one and this one like that, and I'm saying that that is going to be 2 times, that's the 2, and that this u1 squared plus u2 squared plus u3 squared, that is the norm of u squared, and the other one is the norm of v squared. And that is, in fact, given what we showed right here, that is equal to 2 times the dot product of u plus the dot product of v. This is very exciting. Okay, so this thing here, my initial thing that I added up, I have now showed that that is equal to 2 times u dot u plus v dot v. Okay. All right, so there's some algebraic properties here of the dot product. The first one here, it doesn't matter which order we do it in, it's commutative. We have here this one here, left and right distribution. We have here scalar associativity, and we multiply by, if we do the dot product with 0, we get 0, and then here we have another, the dot product is here distributes. All right. Somehow seem to have left and right distribution. Oh, I see. This is the, yeah, it distributes over this, and it also distributes over that. Okay. All right, so let's just make a basic proof of the 2a. It might not be a bad idea just to wind through from the definition of the dot product, wind through and write out proofs of the rest of them. It's good practice, and it sort of gives you familiarity of dealing with these things. So we're taking the dot product u dot v, and then by the definition of the dot product, that looks like this. There it is. That is by definition of dot product. Okay, and I would do exactly the same thing for v dot u by definition of the dot product. That's the definition of the dot product. And then I'm going to simply turn these ones around in the second one here. So this is going to still be v dot u, and I'm going to turn these around like this, u1 v1 plus u2 v2 plus, I keep going, un vn. Okay, why am I allowed to do that? That's because these are just numbers. These are all just numbers, right? u1, v1, u2, v2, all of these things are just numbers, and scalar multiplication is commutative. That's, I mean, 2 times 3 is 3 times 2. Okay. So that's a property we have already established from our scalar arithmetic, and then that indeed is u dot v. There it is. Okay, so we've showed the first one. Highly encourage you to do as much work as you can, work through the other ones, and convince yourself that I'm not lying to you. Okay, now let's talk about something that is getting more interesting, a little bit more, maybe a little bit more non-obvious, or let me just say, you wouldn't necessarily see this right away, I don't think. At least I wouldn't. So let us just see how this works. Imagine me taking two vectors. Here they are, u and v. There's u and v. And I'm going to define or tell you what when I use the word angle. When I use the word angle between these two non-zero vectors, what I mean is the smallest non-negative angle needed to rotate one vector to the other. So what I'm thinking here is this angle right here, theta. So that's the smallest non-negative angle that I would need to rotate u such that it landed on v. So in this definition of what it means when I say the angle between two non-zero vectors, that by this definition, this value theta is going to have to be between 0 and pi. Okay. All right, now here's the cool thing. It is the case, let me just redraw my drawing. There is u and there is v. In this case, I'm going to label this angle here as alpha. I can compute alpha using my ideas of dot product and norm. Okay, and that is, I can calculate it in this way. The angle between those two vectors is the arc cos of u dot v divided by the norm of u multiplied by the norm of v. We're going to prove this in a sec. Okay, I just want to point one thing out when we're looking at this. Notice this right here, that is the unit vector parallel to u. Okay, so this is a non-trivial piece of information that you can, by using, if you're given the algebraic definition of two vectors, you can simply take the dot product of them, you can find their norms, and you can, from that, figure out what the angle between those two vectors are. And we're going to prove this in R2. So what we're going to do is we're going to use this the law of the cosine, which you have seen at some point in your career, probably in, I don't know, grade 11 or grade 12. And we're going to use that in order to prove this theorem in R2. Okay, so I'm going to draw yet another picture. This is kind of the same thing, really. I'm going to label it slightly differently. So let me now call this vector v, and let me call this vector up here u. Those are my two vectors. And then this vector here, oops, let's get that guy there. Sorry. Oh, why wasn't it drawing? Okay, hang on a sec. I've got it somehow in some mode, not in text. There we are. Okay, so got my pen back. There, my pen went away for a sec. Okay, so I'm going to draw that vector there. That vector that I have drawn is v minus u. Okay, and now I have a triangle there. And I am going to associate some letters on this triangle that is like this. I'm going to be considering the length here as I'm going to be referring to this thing here. So I'm going to say here that I'm going to consider the length here to be A, or the side A of this triangle, this as side B of the triangle, and then this one here as side C of the triangle. Okay, that's how I'm thinking of this. I'm thinking of a triangle here with those sides so that I can sort of line this up with my cosine law. Okay, so let us then use that, starting with this guy right here. What is c squared? Well, that actually is the length of c squared, and that is the norm of v minus u squared. And then what is a squared? That is the norm of v squared. And what is b squared? That is the norm of u squared. And then we've got minus 2, and a is the norm of v, and b is the norm of u, and then we've got that angle, cosine alpha. Okay, now we're going to just use a bunch of things we've already convinced ourselves of. It may be a good time to stop the video and say, okay, a major hint of how to go about doing this proof: use the law of the cosine. I've seen now how to, in fact, use the law of the cosine here. Maybe I should work through the algebra here myself and see if I can come out with the result. I mean, you know what you're trying to show. You are trying to show this guy right here. And really, I think you have enough here. It might be not only fun, satisfying, but also you might learn something by doing this yourself. Okay, so I'm gonna take a look here at the left-hand side, and that is the norm is equal to the dot product. The norm squared is equal to the dot product of these two things. We just showed this up above. Okay, where's that? I'm going to convince you I'm not just making new things up. Where did I show that? Oh, right here. Okay, I showed that right there. So we're employing that down here. That is that statement here. And then we're using the distribution, and we will get this here. This is going to keep happening in this lecture. We're doing this several times. We're distributing out like this, and we know that u dot v is equal to v dot u. We in fact proved that one. Okay, so that means we have that the norm of v minus u squared is the norm of v, that is v dot v, minus squared minus 2 times the dot product of u and v plus the norm of u squared. Okay, I am going to now take, I have two expressions here. I have this expression for that, and I have this expression. So I am going to equate this side with this side. So that means I am going to write down here v squared plus the norm of, I'm writing this one first. Write that one first. Minus 2 dot v dot plus the norm of u squared, and then that is going to be equal to, and I'm writing this one here. Okay, and then nice things are happening here. What we have is that this thing will cancel out. This thing will cancel out. We can just simply divide both sides by minus 2 at that point. And that is gone, and that is gone. And what do we end up with? We end up with u, let me be a bit neater. We end up with u dot v, the dot product of u and v, being equal to the norm of u times the norm of v times cosine of alpha. And then we can simply, of course, solve for the cosine of alpha. Cosine of alpha is u dot v divided by the norm of u times the norm of v. Okay, so u and v cannot be the zero vector. And we are done. We have showed this result that we can now use if we ever wish to calculate the angle between two vectors. We can just immediately go to this. We're convinced that it is true. Okay, lots in this lecture. This is, I think, one of our most difficult lectures to date. Okay, coming up next is a important result, the Cauchy-Schwarz inequality. So, I mean, that is simply a statement that the absolute value of the dot product, is less than or equal to the product of the norms. So use an example. I mean, I did this, I'm not going to work out all the details, but just take an example like this. Some very trivial example, like put u like that and v like that. Okay, and then go through calculate the absolute value of the dot product, and then with this u and v, and then calculate the product of the norms and see what happens. I did that, and I found what I got was I ended up with the inequality looking like this. This should give you enough to check your work. Okay, so it worked. In this case, the absolute value of the dot product was 5, and that the product of the norms was 5 root 2. So it turned out to be true in this statement. Of course, It's not much of a theorem if it only works in one case. It's not a theorem at all, in fact. So that's to be expected. But it's nice to see an example when you see maybe something new for the first time. It's kind of nice to generate an example for yourself and see it working. And you may want to ask for what values, or try to figure out for what values of what vectors u and v, what are the conditions on u and v such that the equality holds. So that here's a question for you. When does the dot product equal the product of the norms? What are the conditions? So think about that maybe after you've looked through after you've looked through this proof. Okay, so it's trivially true if u and v are 0. So now we're going to move into the proof considering that both u and v are non-zero. So what we're going to do here is we are going to introduce a function of t, and the function of t is going to be looking like this: the norm of t times v minus u. And that is going to be greater than or equal to 0 because it's a length. And I mean, we already established earlier, norms are greater than or equal to 0. We've also established earlier that the norm of v squared is equal to v dot v. Okay, so let me do almost exactly what I did in my last example, and that will be compute this. Here, let me just write this. Compute this this norm here I'm going to compute this using the dot product. So this is going to look like this: t v minus u dot. This is going to be a square here too. I want that to be a square. So I want to be able to just substitute the square for the dot product. So I want the square there. Again, I mean, we haven't done anything. We're just computing the norm squared using the dot product, and it's still greater than or equal to 0. And we're going to do the distribution and then simplify, and we're going to find out that f of t is equal to this thing here, t squared times the norm of v squared minus 2t times u dot v. Work through these details yourself, please. I've done it, I think, twice in this lecture, so I'm not going to write out all the algebra details, but definitely you should. Okay, this is just like our last example. So there's our function t, and we know that it is greater than or equal to 0. Now we're going to choose to evaluate f of t. I mean, this is true for all t. For all t. I haven't made any constraint on t. This is true no matter what value of t it is. So I'm allowed to pick whatever value of t I want, and this inequality will still be true. So I'm going to choose t equal to u dot v divided by the norm of v squared. An auspicious choice for t. This is a number, right? The dot product is a number. The norm is a number. So this is a number. T is a number. So now I'm going to evaluate my function at this value of t. Okay. So all I'm doing now is substituting in for t wherever it appears, just like a regular function. Substitute that in. And I'm going to get this thing here, t squared. That's this t squared right here, u dot v. This is now t, my choice of t. I'm going to square it. That's t squared times the norm of v squared minus 2 times t. T is u dot v divided by the norm of v squared. And I multiply that by u dot v. That is this u dot v right here. And then I add the norm of u squared. That is very difficult to read, u. And that is greater than or equal to 0, because f of t is greater than or equal to 0 for all values of t. So f of t is greater than or equal to 0 for this particular value of t that I chose. Okay, I do a little bit of arithmetic here, and I get this looking like this. U dot, it's really algebra, isn't it? U dot v squared divided by the norm of v squared minus 2 times u dot v over the norm of v squared. This is squared plus the norm of u squared. That's greater than or equal to 0. Now I don't really care, in fact, about this thingy right here anymore. I've now got an expression, something greater than 0. You might be able to see what's about to happen here. It's getting highly exciting. I'm going to multiply through by the norm of v squared, and that will give me this minus u dot v, right? I'm combining these two right here, minus u dot v plus the norm of u squared times the norm of v squared. That's greater than or equal to 0. I'm going to get rid of this equal sign. I no longer need this. Okay, I'm almost done, aren't I? So I multiply through by, I move this guy here. I'm going to use a different color to emphasize that. I'm going to move this guy over to this side. I'm going to multiply through by -1. When I do that, I reverse the inequality. And I end up here with the fact that u dot v is squared is less than or equal to, that's that reversing of the inequality when I'm multiplying through by -1, and that is less than the norm of u squared times the norm of v squared. And then all I have to do is take the square root of both sides, and when I'm careful, when I take the square root of something squared, that is the absolute value of u times v, and that is less than or equal to u times the norm of u times the v. How exciting is that? There you go. Proof of the Cauchy-Schwarz inequality. Okay, we use this now that we have this little thing, we know that this is true for any vector in any dimension. Now we use this so that we can define the angle between two vectors. We already understand what that means in R2 and R3, but now we want to extend that to R5, R10, R2 billion. Okay, and so we need this little guy here to do that, to ensure that we get something that here is less than 1. I mean, you can see that this Cauchy-Schwarz inequality right here immediately implies that the argument here to the arc cosine is less than 1. So this is the important reason for us to have this right here, is that we now, no matter what dimension of vector we have, we define the angle between them as using this expression here. Okay, next application of the Cauchy-Schwarz inequality is this triangle inequality. So you are undoubtedly aware of this in the two-dimensional model. Let's just draw that. We've got u, and we've got, just draw it roughly the same way I did. We've got v like that, our u and our v, and then what we do is we add those two guys together. So we would move u up here like that, same. So that's also u, and then we would use a triangle here, and this thing here would be, this guy here is u plus v, and what we're saying is if we're saying that the norm of u plus v is less than or equal to the norm of u and v. So we're saying if we walk along this way, it's shorter than if we walk this way plus this way. Okay, that's the triangle inequality. Any two sides, if I add up the distance on any two sides, it's more than the distance on the third side. Okay, we want to prove this. triangle inequality. And this is now, again, we sort of get our intuition and we see what's happening in 2 dimensions, and then we prove it for any value here, n, any value that we like. So this is not just for the 2 dimensions. We're here, and that is going to be equal to u plus v dot u. This is looking familiar. Okay, this is our 3rd time of distributing this out, maybe our 4th time. So this is the norm of u squared plus 2u dot v plus the norm of v squared. Okay, and this over here on this side is u plus v squared. Okay, now I'm going to continue going, and I'm going to say this is less than or equal to, and I'm going to take the absolute value. Why can I do that? Well, because the absolute value of x is always greater than or equal to x for all x. I mean, that's a property of the absolute value sign. Then I can continue going here. This is going to be less than or equal to this. And why can I do that? That is the Cauchy-Swartz inequality. Okay, all right, and here I still have the norm of u plus v squared. Okay, and then I can simply combine these things here, and I see that that thing there. So this thing here, this guy here. I'm going to rewrite this way. Squared. So I'm simply, to go from here to here, I would just expand. Okay, so I am doing that. Then I can take the square root of both sides. And there we have it. The triangle inequality, as a consequence, mostly of the Cauchy-Schwarz inequality. Okay, there's just a couple of small final things that I want to say before we conclude this lecture. With a lot of information in this lecture, maybe have to listen to it in a couple of pieces or come back to it. And that is, I'm going to answer this one. What is the dot product of 2 perpendicular vectors? Let's get the importance here. Okay, the dot product of 2 perpendicular vectors is 0. So that's a major way of telling if 2 vectors are perpendicular. You're given 2 vectors. You're like, are these things perpendicular or not? You take the dot product. If it comes out to 0, you can happily answer the question in the affirmative. Okay, so 2 vectors are orthogonal. That's what that's telling you if the dot product is 0. If we have a whole bunch of vectors, a set of them, and we can take any pair from the set and they are always orthogonal, any pair taken from the set is orthogonal, and then we call the whole set orthogonal. That's what an orthogonal set is. If we have an individual vector and then we have a set of other vectors and we say that u is orthogonal to the set, if u is orthogonal to every vector in S. Okay, so we have a Pythagorean theorem here for vectors, and that is if u and v are orthogonal. This is a major if. Do not do this if u and v are not orthogonal. Okay, so this is easy to show. We have this u plus v here, that is that same dot product, and we're going to distribute again. Okay, clearly this is something you want to be able to do. It's a highly useful tool, and we get this here, the norm of u plus 2 times the dot product of u and v plus the norm of v. And what this thing right here is 0 because the vectors are perpendicular, that dot product is 0, so that term disappears, and we get this, that the norm of u plus v is equal to the norm of u plus the norm of v. That is when the dot product is 0. Okay. All right. Final point to make is what we call an orthonormal set. An orthonormal set is when we've got all the vectors orthogonal, and they are also, every vector in the set has a norm of 1. They're all unit vectors. Okay, so this is more vocabulary. So we've got a non-empty set of vectors is an orthonormal set if everyone is orthogonal to each other and each vector in the set has a norm of 1. Okay, so that's the idea of orthogonal and then orthonormal. Okay, so let's just give an example in Rn of an orthonormal set. So that is what we've already in fact seen. If I take E1 like this, 1, 0, 0, 0, and then I take E2, 0, 1, like that, and I continue going all the way, and I get En and 0. Like that, and you can take the dot products, all the dot products you like here, E1 dot E2, you'll see that's 0, E1 dot E3, that is 0, then you can go E2 dot E3, you can continue through them all, they are all 0, and also the norm of each one of these guys is equal to 1, so they're all unit length, and there's n of these guys here, there's n of them, and there's n vectors here, and here there's n entries. Okay, so we've got an orthonormal set here of size n in Rn. Okay, this is not possible. Okay, if I'm let's just look here, for example, in R2. Okay, I would be like this. I would take one vector. Here it is. There's one vector. I would be now, in fact, I would be looking here for 3 of them because n is 2 in my little case here. And so I've got one vector, and then I say, okay, fine, I'm going to get one that's perpendicular. So I'm going to come here like that and get another one. There's 2. Now, how would I possibly find a vector that's, say, any vector that's perpendicular here is going to be parallel to this one, right? So I cannot find another one here that is perpendicular to these 2 if I stay in the plane. So this is not possible. So don't find it. Otherwise, if you find something that's not possible to find, that can be a problem. Okay, I am done with this lecture. It's a little bit longer than the other ones. And it also has a lot of information in it. So pay careful consideration to the terms and what we've done, and we will be using these concepts quite a bit in the coming lectures. Thanks a lot. See you soon.